So this video is going to talk about Dalton's law. Dalton's law is looking at a mixture of gases and that each individual gas is creating its own pressure and that their individual pressures, when mixed together, make up the total pressure. So if you know the total amount of gas present in your mixture, you should be able to calculate the total pressure using Pivnert. So the partial pressure is the gas, each individual gas would be contributing towards that pressure if it was by itself. And so basically, the moles of each gas are directly related to their partial pressure. That if you take the mole fraction of a gas, the moles of a gas over the total moles present, you should be able to see that proportional relationship with the gas's pressure compared to the total. As we've seen in labs, sometimes you can collect gases because in order to measure them, that can be a little bit more complex since they do not have a definite shape or volume by collecting them through water. And when water displacement is used to collect a gas, we also have to account for the vapor pressure of the water present. So here we have 1 gram of hydrogen and 1 gram of helium. They're placed in a 1-liter container at 27 degrees Celsius. We're going to calculate the partial pressure of each gas as well as the total pressure. So to determine our total pressure or to determine the pressure of each gas, we were going to need to determine how many moles of that gas we have present. We know that the total pressure should be the pressure of each of those gases. It's really hard to do subscripts on top of subscripts. Sorry about that. The pressure of each individual gas contributes to the total. But we don't have the pressure of each individual gas. But we do have the mass, we do have the size of the container in which they've been placed, and we have their temperature. So if we use those pieces of information, we should be able to calculate the pressure contributed by hydrogen and the pressure contributed by helium. So we convert our grams to moles. 1 gram of hydrogen divided by its molar mass, 2.02, gives me roughly 0.495 moles. We take our constant, we take our temperature in Kelvin, and we divide it by our volume. The moles, the kelvins, and the liters cancel out. And so when I do my math through and I count for sig figs, I get that the pressure hydrogen contributed is 12.2. That is the partial pressure in atmospheres of the hydrogen gas. I can do this calculation again for helium, converting the 1 gram of helium into moles, dividing it by 4 grams per mole, and that would give me 0.25 moles, your constant and your temperature, all divided by your volume. The moles, the kelvins, and the liters cancel out. I don't know where the line went, sorry about that. And that gives you, and I'm talking about the line and the R constant. I'll fix that for class. That gives you a partial pressure for helium of 6.15 atmospheres, slightly fewer moles, so roughly like almost half the number of moles of hydrogen, almost half the amount of pressure. To find the total pressure, I could either add all the moles together and plug them into the ideal gas law, or I can use Dalton's law, where if I know the pressure of each of the individual gases, I should be able to add them together to get the total, 18.4 atmospheres. So in this example, I've given you the total pressure. I've told you how many grams of NO2, N2O, and N2O5 were present, and I want to know what the partial pressure is of each gas. And you might be going, Miss Barker, you didn't give me the volume of my gas or the container, you didn't give me the temperature. How in the world do you expect me to do this? Remember that relationship between moles and pressure. And so if I take each of these grams and convert them to moles using the respective molar masses, and I add those moles together, I get my total moles. And now that I know the moles of each individual gas, I can see what fraction of that total each one is contributing. And if I know what the total pressure is, once I know what that relationship is between NO2 and the rest of the gases, as well as N2O and N2O5, I should be able to determine what the partial pressure is of each of these individual gases. So if I want to find NO2, I would take the mole fraction for NO2, which would be its moles, 0.869, over the total moles. And if I add those three together, you get 2.148. And then I multiply that by my total pressure. And so that proportion of the total pressure is the pressure contributed by NO2. 0.396 atmospheres. I can do this again for N2O. N2O would be a little bit more than that because it has slightly greater number of moles, 0.909 moles. And I get, when I do my math through, 0.414 atmospheres. Now at this point, when you get down to the last one, you have a couple of choices. You can do the same calculation we just did, or you can use Dalton's law, that the pressure of each of the individual gases, their partial pressure should equal the total. Since you know two of the three now, and you know your total pressure, you should be able to calculate the partial pressure of N2O5. You can do it that way, or you can keep doing it with the relationship between moles and total pressure. But when you add all three of those individual pressures together, they should equal fairly close. And there might be a little bit of little off due to rounding. They should equal your total pressure. And so we're going to look here at this one where we're collecting a gas over water. We're given what the total pressure was, 1 atmosphere. And we want to know what volume of gas would need to be collected in order to obtain 0.586 grams of helium. That's the gas that we are collecting over water. At 25 degrees Celsius, and this is giving us the pressure of our water, the vapor pressure of water is 23.8 torr. So if we want to find the volume of our gas, and we know the mass of our gas, and we know what temperature our gas was collected at, we only would need a pressure to use our ideal gas law. Again, we can't use the total pressure because it's not accounting just for helium. It's helium with water. But since we know what water's pressure is, we should be able to determine what the pure pressure is of the dry gas, helium. We would need to have consistent units, so you can convert your torrs to atmospheres, or you can convert your atmospheres to torrs. Since your constants in atmospheres, I went ahead and did the conversion with the vapor pressure of water. I don't know why I have 2 decimal points in there, but it should be 0.97 atmospheres. Now that I know the pressure of my helium gas, I should be able to use my ideal gas law. I can convert my grams of helium into moles. I have my constant, I have my temperature, and now I have my pressure with only 1 decimal point this time. The atmospheres, the moles, and the kelvins cancel out, which leaves me with units of liters, and that gives me 3.7. And I did 2 sig figs because of the pressure conversion. Because when I did the subtraction for the pressures, if you take a look up there, you'll see the total pressure had 2 decimal places. The water pressure had 4 decimal places when I converted it. So I would want to round my pressure to 2 decimal places.